All right, so in these last 2 days, we're going to talk a little bit about paleoceanography, building towards what the paleo record tells us about future climate change, or those pieces. And the next time we're going to talk about future climate change. And this is, I'm emphasizing the parts of this story that have to do with pieces of the story that we've talked about, but the tools of paleo, the methods of observation, are quite different. So there's not always an even matchup between those two. And similarly, climate change is not always the focus of oceanographic observations. So a lot of the ocean story we have told is more about like how the ocean works, not how the ocean is changing under climate change. So the overall topic of the class, ocean circulation and climate, has two parts. The circulation part is what we've been spending a lot of time on, and then a lot of the changes we can understand through those circulation pieces we've learned, but some of them are a little bit flavored. So I'm trying to emphasize the places where there's overlap, essentially. So I wanted to talk a little bit about paleo, which is not, which I will say there are other people in this department who know a lot more about it than I do, but I wanted to talk about at least the pieces that touch on the parts that we've touched on. So sometimes this is occasionally the way that I feel when talking about paleo. The Upper Pomeranian, yeah, exactly. Anyway, so, but like, there is this tradition, right, of naming everything by giving everything a name rather than giving it a date, because the conceptual existence of something in the paleo record greatly preceded our ability to date it for a long time. And so they started out roughly guessing with really big windows, but then they knew that this came after that or that came after this, so they gave a list of names, and they said within those names there's these other list of names, and we tell these. So they were doing it all based on the rock record, not based on time. And so now when we study geology, actually the time history is pretty well known. There's some uncertainty in dates, but now we can start to build toward dates, but it's not a clean thing. So, so over the last, so in this side, millions of years ago, so up to 500 million years ago is where all of these pieces on this side go. And then these go up to the 4.6 or 4.5 billion years of the whole of Earth's history. So there's essentially nothing preserved from very few things are preserved from this era. You start to get some pieces, some little bits of evidence in the rock record from here, but it's not great. There's not a whole lot of specificity about what it tells you until you get up into the Phanerozoic, so the last 500 million years. Then there are actually pretty substantial rock records. You can date them, and pieces within there you can start to think about and categorize what's happening. The other piece of this story that's important, so we've talked a lot about what sets up the mean state of the system. So here's where the Hadley cell is, here's the westerlies, here are the trade winds, here's the temperatures that we observe. But how do those change over time? So when we think about climate change, we would like to know what the response would be to some perturbation to the system. One way to learn about that is to learn what the past states that have been visited were like. So what were the things that we think of as forcing? How did those change? And what were the how big was the system response? So we're looking for detection of past forcing and detection of past responses. So all of this gets done indirectly. We didn't have any thermometers in 500 million years ago. There were not actual thermometers. There were things that were sensitive to the temperature, and so we can use them as a proxy for a climate variable. So proxy, like if you vote by proxy, or if someone is your proxy, they're the person who's representing you on whatever you're doing. This is the same concept. This is a measurable variable in the paleoclimate record that has some relationship, we think, perhaps even a quantifiable relationship to variability in the system. So trees grow faster when it's wetter. So the size of the rate of growth, so how fat different tree rings are in each year, gives you a sense about whether the conditions were good for those trees growing. And that's a lot about the water. It's a little bit about the temperature. It depends on what altitude you're at. It depends on what species of tree you're looking at. And so there's a lot of complexity, but a record of tree rings, width versus date, is a proxy for changes in the environment year by year. Many paleo-temperature, paleo-sea level, paleo-moisture, and paleo-biological productivity proxies have been developed. So that's part of the problem with paleoclimate. The other part is stuff gets lost or buried or ruined or destroyed or metamorphosed or after it is laid down. So the farther back in time you go, the fewer records there are. So there's a lot of absence of evidence and evidence of absence and those kind of logical questions. They go back, if you don't discover a particular species, is it because that species was extinct, or is it because that species was not recorded in the record? And so there's a lot of distinctions between absolute likelihood and relative likelihood. So you might find a mass of fossils, and those fossils look there are more of them there than there would have been in that location in the modern, so that's one piece of evidence. But then within those fossils, what's the species mix, which isn't dependent on how many of them, but the relative abundance of one species versus another versus another versus another. So those two pieces are different evidence. So there's evidence for the absolute quantity, and then they're absolute for relative quantities. Similarly with temperature records or moisture records, you might not be able to relate this tree ring being fat equals this many inches of rainfall in that year, but you might say that it was a relatively wet year, or the variance as you go from year to year in tree ring widths is greater or lesser than it is now, which might be a cleaner indication of the degree of climate variability. Does that make sense to everybody? So there's a lot more detective work involved in paleo stuff. Okay, so one of the things that you also confront very quickly is that the paleo Earth was really, really different from the modern Earth. For example, before there was oxygen in the atmosphere, or lots of oxygen in the atmosphere, things were really, really different on the Earth. So in the early atmosphere, we think that there was lots of nitrogen, as there is now, but probably lots of CO2, not so much free oxygen, before there was photosynthesis. And so instead, you have a whole different temperature balance, because now you've got a different atmosphere. And so there is a greenhouse gas effect. There's a lot more CO2. So you might think that would behave like a high CO2 atmosphere now, but there's also a lot of other things like hazes, which don't really exist in the modern atmosphere. They would not be as stable. So it's kind of like smoggy kind of stuff, like clouds that have dusty clouds that have very different properties than modern clouds, which are more compatible with an oxygen atmosphere. So when you get back to that era, things start to get very funny. So that's still before we have a whole lot of stuff, but then once we get to the origin of life and the rise of, the oldest microfossils are somewhere back in the very earliest rocks. So back here in pushing 3 billion years, around there. But then photosynthesis and atmospheric oxygen kicks in about 2.1 billion years ago. And then things that we might actually think of as like an appreciable fossil, like a shell or a fish or something like that, happens up there. And so the development of the spinal cord, central nervous system, somewhere in that territory. So even though we're only looking back in, say, 500 million years, that's sort of also consistent with the whole history of higher life forms beyond, unicellular or very simple life forms. So the fossil record is kind of where the attention starts. That's also where the rock records are better. So this was an example of the anti-greenhouse effect. So anyway, I won't talk about this, but this is essentially the atmosphere was really different. The temperature was really different. The conditions under which life first evolved were really different than since we have had an oxygen atmosphere. And how do we know that there was oxygen and then not oxygen and that kind of thing? So one of the interesting things about the oceans is that they can't hold any iron in them now. So the iron is often a limiting nutrient for life in the ocean. But if you don't have an oxygen atmosphere, then that's actually different. So you can have Fe2+, which is soluble in water, so you can hold a lot of iron in the 2+ form, but if you put oxygen in, and then the oxygen saturates with the water at the top, all the iron comes out because this reaction gets driven this way, and this is not soluble in water. So at the moment, this, this is what we have in the ocean, and this is not soluble, so the iron basically falls through and just precipitates right out. But if you didn't have oxygen, then you can hang out on this side and not have that reaction go forwards. And this would be, so you could have an oxygen-rich ocean as long as there was no oxygen. Sorry, an iron-rich ocean as long as there was no oxygen. So in the sedimentary rock from around the beginning of the origin of so this is one of the key pieces of evidence for the origin of oxygen in the atmosphere. There are these banded iron formations, so they're rusty colored because they've got a lot of iron in them. And the interpretation of this is that periodically you would get oxygen in the atmosphere and all of the iron would fall out and make one of these formations. And then maybe the oxygen level would go back down, you'd build up some more oxygen, and then it would all dump out again. And so these are bursts of essentially precipitating out all of the iron in the ocean whenever the oxygen appeared. And then you go to the modern, and there's no more iron in the ocean because it's been persistently oxygen-rich afterward. Does that make sense? Yeah.
So that rock which is shown as bands.
Yeah.
If I cut horizontal sections, I would get red color, then gray color.
Yeah, so each of these is like a sheet
Okay.
that was laid down kind of at the same time. So that would have been the bottom of the ocean at that moment was that sheet. And then it gets buried by different stuff, and then it gets buried. So older towards the bottom, younger towards the top.
Okay.
So depth is related to age, but not exactly the same as. Okay. So you can also try and figure out when it was cold or warm or dry or wet. And so there are a lot of different proxies for this in a lot of different places. Some of you work on different pieces of this story. But so at the moment, or well, past where we are, there's those little wiggles on the cold side. So those are ice ages coming and going. And the ice ages go back to the Miocene, essentially, and then things stay warm for a while, and then there's a cold burst, and then warm and cold burst, and then warm, cold burst, and then warm. And you can also see that the precision is going down as we go farther back in time because there are fewer and fewer records preserved, and the level of specificity as to what they show gets less and less. But this magnitude of change, the difference between ice age and not ice age, is, or global warming and not global warming, is definitely within the range of possibilities that gets seen over the last, well, certainly over the whole history of the Earth, but even over the last 500 million, 250 million, 1.8 million years. So there's a lot of variability, and then the wet, dry part is kind of a funny thing. So what does it mean to be dry globally? Like, how does that work? Or wet globally? Means there's not any at all, sort of. So the dry side is that there's a slow water cycle, and the wet side is that there's a fast water cycle. Even though we would expect, like, say, the subtropics would always be dry and the tropics would always be wet, the difference is the amount of tropical precipitation could go up and down, and the amount of subtropical drying could go up and down. So one of the key ways in which that happens is that the atmospheric temperature goes up and down. Because when the temperature is really warm, the atmosphere can hold more moisture. And so it is both more capable of evaporating, but also more capable of precipitating. So that's part of the game. So in some sense, these look a little like these, but then they're big hunks of time when they don't. And I don't know what to make of that exactly. So why is it dry in the Cretaceous? That's kind of a strange thing to think of. The Cretaceous is really warm. Why would it be dry? The atmosphere would be capable of carrying a lot of moisture. It's not like there weren't any oceans. I don't know. So anyway, these are the kind of questions you can think about. And then we start to see the onset of, no, I'm going to skip this one. Whatever. Basically, we start to see the onset of ice ages. And that tells us something about the way that the modern system works. So we talked about Milankovitch forcing. So there are variations in the orbital forcing. And in the modern, so the Pliocene, the Pleistocene, we actually see those orbital variations having a response in terms of growing ice. When you go back to previous warmer climates, there isn't an ice feedback, there's a whole different system. And in even before that, there are times when it looked like the whole planet is just socked up with ice all the time. So you'd snowball Earth kind of thing. And once you get covered with ice, it's hard to melt all the ice because there are lots of planetary scale feedbacks where you're just reflecting all of the sun's rays, and it's hard to warm back up from an icy planet. So, all right, we'll talk about a little bit about the evidence for those pieces. Plus, in addition to orbital forcing, on long time scales, on the billion-year time scale, the sun is actually changing. So our understanding of stellar dynamics and observations of other suns that are like ours but younger indicates that our sun would have been faint, so not as bright in the past. Which is a complicated thing, because if you go back in the past and you say, look, it's warm back here, how is it warm when the sun wasn't as strong? And so that starts to make you think a lot about the strength of the greenhouse effect and how the different atmospheric constituents could have led to different kinds of greenhouses, and whether that wet, dry piece, how that affects the cloud piece, how that affects the water vapor as a greenhouse gas piece. There's a lot of changes. So let me see if I can explain how this figure works. So this line is the temperature that the Earth would have if it was just a metal, no atmosphere. It's the radiating temperature. So it's the temperature that the Earth would need to radiate back to space with if there was no greenhouse effect. This is something closer to a surface temperature with a certain amount of greenhouse effect accounted for with a fixed level of CO2 and a fixed albedo. So the fixed albedo affects this one, the fixed greenhouse affects this guy, and then as the sun goes from faint up to bright, you're looking for essentially intersections here tell you where you could possibly sit. So in order to get water above freezing, 273 Kelvin, you kind of have to hang out over in this territory. But how did you do that back here 3 billion years ago when there was definitely liquid water on the surface of the Earth? Why was it there? It's not supposed to be there. According to this figure, it says even if you add the greenhouse effect in, you're still 15 Kelvin shy of freezing. So there's a lot of puzzling pieces of this. So something had to change. The albedo had to change or something. One possible solution is that you're actually getting additional heat sources besides the sun. So geothermal heating might have been part of the story, but it's, if you estimate how big it was based on the cooling rate of the Earth's core, essentially, like how fast did it go from planetary formation temperatures down, it's not enough. And that includes the radiation effect too if you want. But it looks like you had to have had sort of a different albedo of the planet in order to get more sun in. So remember, this figure didn't include changing CO2 and didn't include changing albedo. So if you change the albedo, you could have absorbed more light to begin with. If you change the CO2 level, you could have kept more heat trapped in. Both of them would have tended towards warming. So maybe it was an ice-covered planet, but maybe it was a dusty, black, gross ice that was still absorbing a lot of energy. But you probably come down to think that there would have had to be some kind of greenhouse gas effect. So anyway, so those are sort of deep time conceptions about things that you can think about the climate system, and it essentially convinces you pretty quickly that there's no time when the greenhouse effect couldn't have been important in the Earth's history. And in addition, that the greenhouse effect likely varies a lot. It's not something that could have not varied, even at the sort of most bulk perception of the way that the Earth system works. So now, when we get into the closer to the modern, we start having variations in CO2 levels, either in response to the ice ages or variations in CO2 levels that are driving changes. Maybe that's not such a surprise when you think that the system always had to have variations in those kind of pieces to make sense with what the record tells us. So that's part of the game. In the early days of life, most of life was in the oceans, and in the Cambrian there was an enormous explosion of different kinds of life, all different kinds of creatures, and there was still nothing on land, but there were all kinds of things in the oceans. Here's what the continents looked like right there around that time. So what do we think the ocean circulation would look like? This is a serious quiz of whether we understand.
One large gyre.
Maybe one big subtropical gyre here. And which way would it go? Would it go this way or go that way? We go this way, because there probably still would have been westerlies and easterlies. And so it would have still been a subtropical gyre. Maybe there's a little small subpolar gyre here. And there probably would have been some subtropical gyres here and here and here, and these kind of like inverted Indian Oceans. And maybe a subpolar gyre down here. What about up here? There isn't a continent to block it, but there probably still would have been some kind of zonal structure. So something like an ACC, and then who knows what happens up here. We don't really have a bare pole to think about. On Jupiter, now that we've seen the pole of Jupiter, there are all these crazy eddies that just kind of hang out up there. And in some sense, that's what the Arctic is, except they're really small hard to observe, and there's ice on top of them. But, so who knows, maybe there'd be an eddy-filled sea on the top.
Are we sure about the winds for this kind of Earth? Because land gets heated and cooled at a different rate than the ocean.
Yeah, so the monsoons definitely would be different. The ITCZ, rather than being a little bit to the north, probably would be a little bit to the south for almost the same reason. Like it goes to the land side rather than the other side. But the easterlies and westerlies are kind of hard to avoid because essentially your radiation is still going to be most concentrated in the tropics, and so you're going to have ascent here. And if you do that, then you tend to have a Coriolis. Then you have ascent and then descent off the equator. You're going to tend to have the Coriolis, so you have the trade winds. And unless the rate of rotation of the planet changes, or the amount of evaporation changes drastically, which I guess it could, but this is not an ice-covered planet, so probably not. Then you tend to have storms across the westerlies in the same way. So whether you have an aquaplanet or a planet with random, so if you do simulations of a planet which is an aquaplanet, it looks still kind of surprisingly like the modern winds broadly. Or if you do with random continents, it changes the monsoon, but it doesn't change those basic easterlies and westerlies. So seasonality would be very different, but not the basic structure. Other planets in the solar system have different things. So Jupiter has multiple bands of zonal jets, going one way, going the other way, going one way, going the other way, going one way, going the other way. And so does Saturn. They're much bigger, their rotation rate is different. So essentially the Rossby deformation radius and the beta containment scale, so the effects of rotation and the variation in rotation on the jets are different. And then other planets, there's just kind of a Hadley cell that fills the whole of the planetary atmosphere. If you're on the slower rotation side, then you don't have that failure of meridional transport to stay stable, and it doesn't break down into storminess the way it does here. Okay. So when we get into this warm period, that's when we had the dinosaurs. That's when we had dinosaurs everywhere, even north of the Arctic Circle. So dinosaurs don't really like cold weather. Neither do birds, or most birds. So the idea that you had dinosaurs north of the Arctic Circle and crocodile ancestors north of the Arctic Circle and palm trees, things like that north of the Arctic Circle means that it is possible on this planet to have a pretty warm polar region. There's a lot of activity in the the isotopes of carbon and also carbon dioxide. So you might think that there was a lot of greenhouse gas warming, and this part is an indicator of volcanism, I guess, in this case. So where is that carbon coming from? It's coming from a different kind of plate tectonics than we have now. So faster spreading rates, faster subduction of carbonate sediments, increased CO2. So there's a lot of feedbacks in the atmosphere and in the carbon cycle that are not like the present. That maybe is the explanation for the warming over that period. And so if you start thinking about the dinosaurs, then you start thinking about the fact that maybe the dinosaurs aren't here now. And so one of the other things you can construct from the fossil record is massive extinction events. So there's the Permian, the Triassic, and the Cretaceous, or the KT boundary, this is the one that the dinosaurs die off. And so this is a percentage, extinction percentage. So what percentage of the taxa, I'll be that vague, suddenly disappear from the fossil record? So they can't, depending on how good the rock record is, you may not be able to preserve species level. You may only be able to preserve genus level, or maybe only class or phylum. So it's difficult to be sure when you have relatively few records how much, it's not like you can go out and take a census of all the animals and see where they were. So you have to build on that kind of reconstruction. But even with those uncertainties, there are places where the extinction rate spikes over relatively short periods of time. The extinction rate at present is not shown here, but it is about this high. It's similar to where we were at that level. So that's partly because of human development and partly, we think, because of climate change. Okay, so whatever. People have heard about Chicxulub and the meteor smashing in. So do people know how they figured this out? Yeah.
You can find like a layer of it's like fused glass over the whole Earth.
So there's fused glass, and they just found evidence of a big wave, which I don't know exactly. Didn't fully understand and it was whatever. They also found high levels of iridium, I think. So the impactor itself must have been very rich in iridium, so you can detect it as a big spike in iridium. And so those pieces were going around, and nobody knew what that was all from. And then they actually found the crater and dated the crater, and then things got a little more clear. Yeah. All right. Well, all right. Let's go a little faster. So after this big impactor, things start to change. We start losing the CO2 in the atmosphere. There is some mountains get created, which may affect the carbon cycle through weathering, and it might also have changed the climate patterns, the patterns of the way that the atmosphere works. Like, so if you make the jet stream swerve around the Himalayas, that's going to change a lot of other things. So there's a lot of conjecture about exactly how this all works, and there's a fair amount of modeling of different pieces of this story to try and see how things work, mostly on the atmospheric side, not so much trying to figure out how the oceans change. But then, once you get into the relatively recent past, the Quaternary and the Pliocene, we start having glaciations, and things start to look like, so maybe this has to do with the creation of the Himalayas, maybe it doesn't. Maybe it has to do with the closing of the Panama Isthmus, maybe it doesn't. Maybe it has to do with changes in the Indonesian through flow, maybe it doesn't. There are a lot of papers kind of trying to figure out the consequences, though, by digging out holes through things in climate models and then seeing what the climate looks like. It's an interesting way to see what the climate models do. I'm not sure that it's an interesting additional piece of that story. Okay, so once we get into the Pleistocene is when we start having ice growth and decay. So, and in some sense, this was the original paleoclimate story. This is the original paleoclimate story because this is the one that, so a bunch of people who were essentially biblical scholars were going around looking for evidence of the Great Flood. And instead of finding evidence of the Great Flood, what they found were lots of scrapey things like this that looked like you had dragged a lot of stuff across the rock face, or ridges of anomalous sediment that don't seem to make sense how they got there, or really, really mixed pebbles that come from rocks that are very distant in origin, so they can't possibly have been made there. They had to get dragged there from somewhere else. And they're big enough that you can't imagine how wind got them there. Or certain classes of soil that also don't have an easy mechanism for creation in where they are. And so once you get all these pieces in mind, you think there must be some massive agent of relocating soil from place to place and small rocks, and that in the process seems to cut these deep grooves into whatever it's going over. And if you live in the Alps, this would be familiar to you and seeing the way that small glaciers work, and so maybe you would imagine larger glaciers. And that's the process that they came to. Then, but that doesn't tell you exactly how many they are and what about the dating. And so one of the big breakthroughs of, I guess, 20th century paleoclimate is using isotopes as markers of variability of the system in the past. So isotopes are a good marker. Well, so this is stable isotopes are a good marker because they don't change very much, and they are chemically the same as their partner. So isotopes have more neutrons, right, or less neutrons, I guess, and they behave. So the isotopes of oxygen, you could have the oxygen 18 or oxygen 16. So they have just different numbers of neutrons, but they have the same number of protons and electrons, so they react the same way. They both could be in water. They both could be in carbonates. They both could be in whatever would have an oxygen, and it could go either way. Some processes will select between them. Things that involve evaporation will tend to select for the lighter elements to evaporate first. Things that involve freezing or trapping, slowing down, will tend to prefer the heavier ones. Cloud formation, precipitation, evaporation. So you get sorted then where you have relatively lighter elements in the, let's see, so you get, so as your ice sheets grow and decay, you're essentially moving around the ratio of the heavy and light oxygens. And so because they then will just get encased in whatever they're in, if you have a sediment that is, say, a plankton, when a plankton has got a lot of heavy stuff in it, it means that that's a time when there was colder water. That means that there is so essentially the point is that you have a record in the way that you have the isotopes and where they are in the system, and from that you can infer whether there were big ice sheets, little ice sheets, and then secondarily, when you form certain kinds of planktonic shells and stuff, they will respond to differentiate themselves from the environment they're in. So there's a change in what the isotopic ratios are in the ocean, and then there's also a temperature sensitive change in the way they're recorded in the shells. You try and recreate those two pieces, and you end up with a time series of del 018, so the anomaly in 18 to 16, that is essentially a record of whether you have big glaciers or little glaciers. So warm in one direction, cold in the other. And so then you can go back and say, well, I saw those little etches for where my ice ages were, which one was it? And then you start looking for anomalies on this side and figuring out which one is the one that's the one that you are looking at. And then you also, if you are smart enough to put this together with the Milankovitch cycle, you can figure out what the orbital configuration of the Earth was in, and therefore what the surface forcing was in different places at different times. Milankovitch, so we talked about this a little. I don't think I want to go through the celestial mechanics again. Let's skip over this. But there are variations in that. Okay. So, does that explain everything we need to know about the way that the climate system works? Not exactly. So, here on the top is the Milankovitch cycles for 65 north in June. And you can see it's kind of a wiggly record and goes back 400,000 years. And then the bottom is our del 018 record that we just discussed. And so this doesn't look like that very much. It looks sort of like it. And you could say that if we go to the obliquity band, there's a lot of phase relationships where this one is going one way and that one's going consistently the other way. But then in the eccentricity band, there's a whole lot down here, and there's almost none in there. And then in the precession band, there's some signal in both. Sorry, this is a Fourier decomposition of the signal above and below. But you certainly wouldn't say that there's a proportionality of the response to the forcing that's the same or even a linear relationship across those bands. So if the Earth was just a reservoir of heat, like just a brick that heats up and cools down with the surface forcing, you would actually expect that this and this and this and this and this and this would all be proportional to each other, and they'd be proportional with a different proportionality coefficient at different time scales, because more persistent heating would tend to heat up a little bit more. There'd be a proportionality factor that would be a function of time scale, but there wouldn't be systematic differences. There wouldn't be this one is there and not there at all on that side. So this is one of the cleanest demonstrations that there is a nonlinearity in the response of the Earth system, essentially because this record doesn't just amplify that one. Does that make sense to everybody? So what's the nonlinear process then that's refusing to amplify?
There are a bunch of feedbacks in there, like greenhouse gases.
There's greenhouse gases. So if it gets warmer and then that changes the effect of this because it changes the heat trapping, that would be one. If the ice grows and changes the albedo, that's another one. So those kinds of systematic changes to the system where you're not only changing the system, the record of the response, but you're also changing the sensitivity of the system to the forcing, is exactly the kind of nonlinearity that would make these effects big. Or if you change the amount of cloudiness with temperature, that's another one. If you change the AMOC in response to freshening, that's another one. So there are all of those kinds of systematic switches will change the sensitivity of the system. It's not just heating up and cooling down the same way all the time. So the fact that the response function, at least as measured through isotopes, doesn't look like the forcing function is an indicator that those effects exist and that they're strong. All right, let's get that. So ice albedo feedback is one. Biological feedbacks, river discharge, and so weathering, and then continental shelf exposure, clouds changing the albedo, records of clouds and that. All right, so but here's one that actually does directly affect the way that we're thinking of. So this is now zooming in on one part of the recent deglaciation, and so this is a history of snow accumulation, and so the typical scale is going along like this, and then there's a little blip where it's low, and then it goes back up, and there's a little blip when it's low. So this is during the process of deglaciation. So you've got a huge Laurentide ice sheet that's covering all of North America, and it's melting back. And the way that a glacier works is that it melts part of the year or part of the regions, and then it's getting snow in other parts, and it's flowing together. So if you have jumps in the amount of snow, then you're going to have rapid retreat or not, depending on the amount of snowfall. And you might have changes in snow because you'd have changes in the temperature. It could get too cold to snow. The air could dry out essentially. Or because you just have a change in the patterns of where the warm stuff is, where the wet stuff is, by changing the weather. So in this event, what is seen is that the snowfall was changing, so that's showing that there was some weather changes. There was also big bursts of fresh water. So inland lakes that had been part of the glaciers that were melting rush away to the coast, and exactly which path they take and exactly where they put the fresh water is not so obvious, but there are some records trying to reconstruct that. And one of the things that happens is that it looks like the meridional overturning circulation in the Atlantic gets shut down after some of these bursts of fresh water. So what do we expect to happen when the AMOC shuts down?
Cold northern hemisphere.
Cold northern hemisphere, cold North Atlantic region. And so in some sense, like, so things are warming, and then it stops for a little while, and then it starts warming again. So it's a little bit more of a spotty recovery. And that maybe is not, that's an interesting part of the deglaciation process, but what's the relevance to right now? So if we're warming now, and our Greenland is melting, there's the possibility that we could have a similar kind of bursty release of fresh water that would then shut down the AMOC for a while and then have it come back. So it at least puts the possibility in that AMOC variability together with ice sheet changes is possible, that those two could be linked to each other. And once you get them, the persistence time scale here is like 1,000 years. So it's effectively permanent on human time scales if that happens at this magnitude. And it's because once you start cooling again, then you're changing all the weather in the local region, and then you're changing the ablation versus accumulation balance. It's part of the story of how an ice sheet would retreat. It doesn't just neatly melt the state, melts a little more because it's warmer. It could have local feedbacks that change the history, the way that it interacts, and those feedbacks might not even be within the ice sheet. In this case, it seems to hook into the ocean circulation, and from the ocean circulation into the atmospheric circulation, and then back into the precipitation, which impacts again the ice sheet. So it's a linked chain of events that goes through. So, whatever, more maps of that. Okay, so now, all right, if we take that then as the story, so what's our big picture of paleoclimate? Things have changed in the past? Yes. Things have changed a lot in the past? Yes. The past gives us some evidence of the potential responses of the system. Is there an exact analog, though, for what's happening now? Probably not. So what are the difficulties in making that analogy? The time scale changes. So right now we're putting more carbon faster than we know of at any time in the recent past, and possibly at any time ever, because we're not behaving like a natural process. We're not just speeding up weathering a little bit or slowing down weathering a little bit. We're taking stuff that's presently buried, pulling it up, and burning it. So we're greatly accelerating the process by exposing stuff in a way that at a rate that natural processes would not expose it, right? In addition, so like the Younger Dryas, what's different about the Younger Dryas versus now? So the Younger Dryas, the CO2 was coming up, the ice sheets were moving back. But it's different. What's different?
It's faster, so the climate is not stabilizing in the time frame that it's still accelerating.
Yeah, so the deglaciation took a longer time, thousands of years. This is on the hundreds of years time scale that we've gone a degree, heading towards 2 degrees towards the positive, as opposed to a couple thousand years to go 6 degrees from the negative. But also the mean temperature is different. So that was global warming when you were covered in ice sheets, which is a very different system than global warming when you're not covered in ice sheets, because the ice albedo feedback is just different. There's not snow everywhere. There's snow in some places in some seasons. So changing the snow now has a different impact than changing the snow then. It's at a different latitude, it has a different effect on the sun. Plus, the biological response is really different now because we actually have soil in Canada, not just ice sheet. So there are biological feedbacks that are in play now that weren't present then. So even if the ocean circulation is sort of similar, even if the wind patterns are sort of similar, the feedback through the land ice, the feedback through the sea ice, the feedback through the land biology are all really quite different than they were then. So we should expect the sensitivity of the system to changes in CO2 to be different. Plus, in the deglaciation, I don't know, maybe this is sort of, we think that the carbon dioxide change was in response to the deglaciation as opposed to a driver of the deglaciation. So the deglaciation was being driven by the changes in the orbital forcing, and then the CO2 was responding. So it's different to be changing the CO2 and having the CO2 be forcing the temperature response, even though a lot of the same CO2 feedbacks are kicking in. So we're releasing some CO2, conceivably more CO2 builds up because more CO2 as you're warming is what the system wants to do. Certainly more water vapor as you're warming is what the system wants to do. So the greenhouse gases are going up faster than the emissions. So how does that, so that's a different part of the system, whereas the greenhouse gases before were not the driver, they are the responder. So it's different in a bunch of different ways. So it's not an exact analog. And even if you go back to the places in the past where the mean temperature might have been the same, like the last interglacial was a degree or two warmer than present. And so you could say, and it was far, maybe the glaciers were in kind of a similar configuration as the way they are now, but the orbital forcing then was really different. So it's still not an exact analog. So we want to be careful about using the past as an exact duplicate of the present, but it certainly does illustrate what some of the possibilities are. Does that make sense? Okay, so, all right. So present day as of 2011, because I was pulling this out of the 2013 IPCC. Soon we will update this. Anyway, atmospheric greenhouse gases exceed the range of concentrations recorded in the ice cores during the past 800,000 years. Oh, we also didn't talk about the fact that along with the isotopes in the isotopic record that's in the ice cores, you could also, or in the sediments, the ice cores have bubbles in them, and the bubbles trap the atmosphere. So there's a record of what was in what the atmosphere was like from the little bubbles. So you can go back and figure out the concentration of methane, nitrous oxide, or greenhouse gases to some specificity. And the present, so if we pull all of those pieces, so here's a reconstruction of sea level, which is partly a reconstruction of the ice sheets, so that's part of the isotope record. Here's the benthic oxygen isotope anomaly, which is a deep sea isotope record. The Antarctic isotope record, or temperature inferred from that. The tropical sea surface temperature, which is from a different set of proxies. The CO2 from the ice core bubbles, and then the orbital forcing above. So what do you see when you look at these?
Poles in the deep sea tend to change a lot more than the tropics.
Sure, yeah. The tropics are a little more stable. And the poles, and do any of them look like the orbital forcing? Not exactly, right? So maybe you can do some kind of the triggering event is a combination of those, but it's certainly not a linear response to any single one of those bands. Doesn't look like it's in phase with any of them, so it has some nonlinearity in it. Which makes sense because the sea level record is a measure, in some sense, of the ice sheets moving, coming and going. And so there are lots of feedbacks inherent in these pieces of the story. The CO2 is also in phase with the comings and goings of the ice ages. So the CO2 is either responding to or driving, probably more on the responding to side. So, so what are the numbers on the CO2? Can anybody see? 280 to 200. So what is it now?
420.
Yeah, so 412, so up here. So not without rival in that 800,000 year record. So that's what I mean by being outside the range. And if you did it with nitrous oxide or methane, it's the same story. That it comes and goes with the ice ages, but it doesn't hit anywhere near the values that we have now. Okay, do I have that one? Oops, I'm going backwards. That doesn't help. Oh, here we go. So here's modern record, and here are a bunch of different other reconstructions of CO2 going back over millions of years now. And sorry, cut that guy off because it's not, I think that's deeper time, but it doesn't matter so much. But until you get back here, order 3 million years ago, it doesn't look like anything rivals us. These are a lot more uncertain than the ones in the last figure. Sea level. So what's sea level doing? Sea level is going up and up and up and up and up. So, but how big is that swing on sea level axis? So between an ice age and a not ice age.
It's like 120 meters.
Yeah, it's like 100 meters. So the fact that we get panicked about sea level changing by a meter, there's a whole lot of precedent for sea level changing by an awful lot more than that. And that's both from kind of the budget of isotopes and figuring out how much ice there was versus not ice, but you also can see it in that there are places where the sea level has been higher than it was now, and the sea level has been much lower. So there are features on the seafloor that are indicative of when it was exposed as land. So you find rivers below on the shelves, essentially. So you find structures that only were explained by when it was exposed. So there's a lot of evidence that the sea level changes are big, but when you borrow stuff and add stuff to the ice sheets. So that's part of what we shouldn't think that the ice sheets are as stable as you might be. And there's dust accumulation at the top. All right. So sea level picture. Is this the sea level? No, this is just deeper time CO2. This is the last panel from the last one. So when you go back here into Cretaceous era, then the CO2 levels get much, much higher. So things were quite different then. So is CO2 of 410, 500, 600 an extinction level event? Like of all life on Earth? Probably not. There was lots of critters living over here. Is it a really big change that is going to change the whole structure of the planet? Yes, it is. So there's a distinction there that's important to keep in mind. All right. So here's one of the many multiple hockey stick figures. So this is basically just showing temperature, and I mean these are probably things that you guys have seen before. Essentially, there's lots of different ways of reconstructing the temperature from paleoproxies. Not all of them line up. They all line up pretty well in the modern, but that's kind of not a coincidence. But then when you go back, like, was this period, the medieval warm period, warmer than the present or not? Like, those are questions that you might want to know. This little ice age, Is global warming dramatic because we're coming out of the little ice age and going into something warm, or is this warming actually the bigger part of the story? So, a lot of this is important in thinking about how the context for which the modern warming, where we're supposed to go. This only goes up to 2000, not up to 2014. But anyway. One of the big advantages of this is that this is recent enough history that we can simulate it. And so we can learn whether the climate models that we have for doing, and weather models that we have right now, can they actually do this? Do they reproduce this part? Do we understand both the forcing mechanisms, but also the sensitivity of the system well enough to rerun the last millennium and get the answer right? So this is an example of that. So the gray is the paleo reconstruction. So it's basically a probability made out of those spaghetti, of the data that goes into those spaghetti. And then the red and blue are different simulations of northern hemisphere temperature. And so as you can see, the red and blue plus their uncertainty or variability window pretty nicely sits within the observations and even gets these sort of like little jumps between volcanoes. Right. So the blue one has weaker solar variability and the red one has stronger solar variability. So the other thing that's trying to be illustrated with this is that it's not, the solar variability is not the story of what set the temperatures over the last 2,000 years, or it's only part of the story. So in one little bit down here, you get a little bit of deviation between those two, but for the most part, they're together. So it's the external forcing of things like the changes in orbit is part of this a little bit, but changes in greenhouse gases, volcanoes, are the changes in the ice sheets are bigger pieces of the story. Yeah. CE, so common era. So this is year 2000 is the way to read it. So this is the year 1000. So this is that's the last millennium from there to there.
But I thought paleo means, in general, it means like thousands and thousands backward.
So it can. So that's exactly the question is like, how far back do you do paleo? So in those, because of all the complexities of the paleo proxy reconstructions, you start getting more nervous about the quality. So you can say things are relatively warmer, relatively wetter, relatively drier, or sometimes you get a direct record like the ice bubbles having the atmospheric concentration. So sometimes you have direct records of pieces of the story, but you have a hard time doing something like constructing northern hemisphere temperature when you go back. So the last millennium, because we have tree records from all over the northern hemisphere, we can actually do this pretty well. And so that means that this is actually a real test of model skill and reproducing it, as opposed, because in the more recent past you get increasingly more quantitative, and the degree to which you believe these are actual numbers in degrees C rather than Delo 18 or something else that's indicative of warmer or colder, but the conversion factor isn't so obvious. Bum, bum, bum. Now, polar amplification is another piece of this story. So for those of you who took my IPCC class, this is whatever. This is a terrible figure. It's very hard to understand what it means. But let me just explain this in words. One of the pieces of this story is when the Earth warms up, which part warms up first? So, as you would expect from the ice ages to not ice ages, the ice has a lot to do with it. The polar regions have most of the ice. That's a big part of the story. So the feedbacks that are inherent in that, both the land ice albedo feedbacks, the sea ice albedo feedback, the air-sea exchange of heat between so the ocean is pumping heat towards the north. Does it come back out into the atmosphere and warm up the surface, or does it stay in the ocean? It really matters whether you're sealed off by a layer of sea ice or not. Even when the ocean is relatively warm and could still lose some more heat without forming ice, if it's capped with ice, it doesn't have the ability to do that. So you can get a deep warm layer, which is a warm salty layer below the surface water that's at freezing, and that deep warmth may not be able to get back to the atmosphere if you're sealed off with sea ice. So in a lot of the Arctic, that's actually the situation. It's warmer when you go deeper, but that warmth doesn't actually come up and melt the sea ice because it's trapped by the sea ice. Both because there's no mixing, because the sea ice is turning off the winds in terms of mixing down into it, but also because the air-sea interface is insulated by the presence of the ice. You don't get direct exchange of sensible and latent heat between the atmosphere and the ocean. So, for all of these reasons, the polar feedbacks are very strong. So when you warm, you tend to warm more in the poles than you do elsewhere. When you cool, you tend to cool more in the poles than you do elsewhere. So the polar amplification of climate change is one of the big signals that you find when you look around. And this is supposed to show you in paleo records that that's true, except I find it very hard to understand. So we talked about this one last time with the sea level picture. Essentially, the sea level rate of change that we see now, so 1880 to 2000, or really 93 to present when we have satellites, is faster than anything else we've seen for 3,000 years. So how do we get sea level reconstructions? Does anybody know? We talked about it a little bit. So we talked about it one way, we could get it from the isotopes, because we basically, global mean sea level, it's either in the ice or it's in the ocean. So we can do the ocean mass exchange through isotopic measures. What about ocean thermal expansion? That's part of the story too. Do we have a paleo proxy? You know, what kind of paleo proxies would you imagine would tell us about past sea levels?
Maybe coral reefs.
So coral reefs, because coral have to live right just below the surface. So they tend to grow more what they're on is subsiding, and they tend to grow less if you get exposed, and then they'll die and then start again below. So if you know the height of the coral reefs, you know the local sea level pretty well. Similarly, salt marshes, the marsh grasses can only grow in places where they're sometimes in the tide and sometimes in high tide, sometimes in low. So they have a very narrow range of specificity. And when they die, they're recognizable in the fossil record. So you can figure out what height the salt marshes were at as you reconstruct them back. Wave cliffs are another thing. So when you have waves impinging onto a rock face, they'll dig out a hole because there's so much energy coming in. And then if you have tectonic uplift of that wave cliff is now preserved as a historical feature as it gets lifted up and up. You then have to figure out what the tectonic uplift rate was, which is another problem, but if you can do that, then you end up having it. Archaeological features for this kind of time scale, you actually can figure out where were the buildings, where were the docks, where do they have boats? Like that is also another piece. So as those move in and out from shore, you can figure out what the sea level was at different locations. So each of these little dots on here is one of those, and I think that the greens and colors are telling you about different pieces of that story. So, paleo sea level data with the relative sea level removed. So light green is from Iceland, purple is Nova Scotia, bright blue is Connecticut, blue is Nova Scotia, red is the United Kingdom, green is North Carolina, brown is New Zealand. Paleo sea level data from salt marshes. So this is the salt marsh figure. And then, let's see. And then this is the tide gauge record. So, and I think this is actually the tide gauge record superimposed on the salt marshes. So, or maybe that's the mean. This is the blue one. God, these things are so. Different salt marshes. A blue time series with uncertainty. Yeah. All right. So that is the tide gauge record superimposed on top of the salt marshes. So there's some fair agreement between the salt marshes and the Tongue. Okay. So each of these guys, right, gives you some variability, but you can also take those melting glacial to interglacials and convert them into rates. So the present rate of sea level rise is that higher than previous rates. So even though we saw that the glacial to interglacial change was 100 meters or so, the rate was ballpark 10 millimeters a year. But then some of these bursty events, the meltwater pulse at 14,600, so another one of these bursts as the deglaciation occurred, was up near 45 millimeters per year. The 20th century is down here. Satellite altimetry is down here at 3. The projections, the last 2 millennia is down there 1. 20th century is 1, so this is just zooming in on these guys. So in the last 2 millennia, the 20th century is bigger than we saw, and the satellite altimetry era is bigger still. The projections for the rate at 2100 are closer to this. So even though that 100 meters change is big, it was over a relatively long time, but the rate was still faster than what we're seeing now as the ice sheets left. But we are expected to approach this level toward 2100. So if that AMOC shutdown mechanism depends on the rate at which you were dumping meltwater in, that's the kind of thing that would start to kick in at that stage as being a potential piece of the story. So, okay. We're going to come back to all these pieces. So this is maybe did we talk about this one yet? In here? I don't think I know we talked about it in the IPCC class, I don't know. I don't think we did here. So this is, think so? So remember that this is the sea level rise from different components of the system. And this is a projection of what the sensitivity would be. So remember, our sea level rise was 1 part thermospheric expansion, 1 part glaciers, kind of 2 parts ice sheets, Greenland and Antarctica. So this is a projection trying to figure out what those different contributions would be. And rather than as a function of time, this is as a function of temperature. So you raise the temperature and then you let the system equilibrate to that temperature. You raise the temperature and you let the system equilibrate. So if we warm up the Earth 2 degrees, which is what we're supposed to do, or better, through the Paris Accords, then these are the level of sea level rise you'd expect. So this is the level of sea level rise from thermospheric expansion, order 0.42 meters per degree C. Glaciers is kind of 0.3-ish. And then Greenland is really interesting, we'll come back to that. Antarctica is order 1.2 meters per degree C. So if we warm 2 degrees, we get 2.4 from here, about 1 from there, about 0.3 from there. So we're talking about like 4 meters to get to 2 degrees over those 3. But look at Greenland. Greenland, if we stay under this jump, we get, less than 1 meter. And if we warm beyond this jump, we get 6 meters. So Greenland has an unstable tipping point. So is this part of the mechanism that led to this? I don't know. I mean, it's the kind of structure. Are these two inconsistent with each other? As you're melting away an ice sheet, does it go all smoothly, or does it go in fits and starts where it has stable points and then it quickly retracts? That's part of the worry about the whole system as we go into changing. And I will say that this one is not all models reproduce this, and not all models reproduce this in the same place. So this is not necessarily part of the future. All right. The last thing I want to talk about where we quit is El Nino, which is, I don't know. So, Hans and I were just talking about this earlier today. Is El Nino a good thing to think about when you're thinking about climate change? Or is El Nino really, really hard? So, El Nino is really, really hard. Is the simple answer. El Nino is hard because it's hard to predict when it's coming, and it's also hard to predict how strong it's going to be. But Kim Cobb at Georgia Tech has spent essentially her whole career trying to capture coral to reconstruct the strength of El Nino. So she goes around all the different islands that are in the path of the cold tongue and collects them and then dates them, and then a coral might live for 200 years. So now you have 200-year record of El Nino, some 200-year window over the Holocene somewhere, and then you find another one and another one. And this is the reconstruction that they get over the past 7,000 years. So each dot on here is like a coral. So it might be a 100 to 200-year record. And then they take the variance in the month to month of, so corals incorporate isotopes into their shells, and the way they do it depends on the temperature of the water and also the salinity of the water they live in. So there's a record of the variability from year to year of the temperature and salinity. So you can infer what the ENSO strength is during the lifetime of that coral. So here in the 3,000 to 5,000 years ago, it looks like the ENSO was weaker for a while. Here in the recent past, it looks like maybe ENSO was stronger. And I thought they had one on this figure that was, went all the way up to present. Oh, here are 20th century corals, which are showing more recent records of just like decade by decade breakdown. So the difficulty is that there's a lot of noise. Some of these are really, really high right next to ones that are really, really low. So is it that one coral was living somewhere special? Is it that the corals have is it that El Nino is wobbly on century by century, which it definitely is? So what's the right explanation? And so what they try to do then is to make a histogram of the differences. So if you compare, say, 6,000 to 7,000 years ago versus 0 to 1, so they're trying to compare this part versus this part. Are those actually statistically significantly different? And in that case, it doesn't look like they are. So here's the 95th confidence window. And so the typical differences all are in this kind of territory. Whereas if you compare the modern coral versus all of the fossil coral, so this record versus all of those records, then it looks like you do actually cross the threshold that the modern looks somewhat different. But it's still pretty hard to see when you put models together with the fossil corals together. Like there's still a lot of uncertainty in the ranges of changes. So, and different models disagree with each other pretty substantially as well, which makes it even less certain as to whether we know what we're doing when we run them with models. So as of this paper, circa 2013, this one is a pretty substantial result that the modern does seem to be different, but we don't have a sense of why that is, because the models are not sufficiently in agreement so as to figure out the mechanism underlying this. So that was, and I think probably still is, the state of the art on El Nino story. Let's see if there's anything else to say. I don't know. Okay. That's the last bit. Oh, this is one fun piece. So, in case you're worried about ice ages, we're not going to get one. So, one thing that we have done with global warming is we're definitely not going to be able to get an ice age for the next 1,000 years. So, we spent a lot of time talking about ice ages. The positive spin, even if we were to be forced toward one, we're not going to get one because of the greenhouse gases. All right. So next time, we're going to talk about just a few more indicators of the modern system, and that will be that.